Hello friends, so today we are going to continue from the yesterday. Yesterday we solved some question about the rotational motion, and today we are going to solve further the remaining questions. And in the first part, or rather in the first question, it states that a solid cylinder of mass m, radius r, is attached to a spring of spring constant k through its axle. If the cylinder rolls without slipping, determine the frequency of its oscillations. So in this case we are given that we can just draw an approximate figure for that, and suppose we have a cylinder and this is the axle and the spring is connected to this axial point, and spring constant is given as k, and solid cylinder is having a mass of m, and its radius is given as r, and we are supposed to find out it rolls without slipping. We have to determine the frequency of the oscillations. So in this case we are given that we have a solid cylinder and solid cylinder is having a mass that is a capital M, and radius is given to as capital R, and we can write the formula for the moment of inertia about its central axis, or we can say the axle. So we can say the moment of inertia about its central axis, or we can say the axle is suppose is I, and this I will be equal to over half mr square, and it is said that the cylinder is rolling without slipping. So we are given that cylinder rolls without slipping, and if we assume that the center of the cylinder moves by a distance of over x, okay, so the cylinder and rotate by an angle of theta, and you can write that our center moves a distance over x, and cylinder must rotate through the angle of theta. Therefore we can write that our x is equal to r times theta. Okay, arc length is equal to our linear distance, and if we differentiate it, so we get this as our x prime will be equal to over r of omega, and if we do its double differentiation, then this will be equal to r times alpha. Okay. And now we can find out its kinetic energy, and kinetic will be of two, translational as well as the rotational. So we are having that our kinetic energy has two parts, and first will be our translational, kinetic energy. Let us call this as T translational. Then this T translational will be equal to over half m and distance and its derivative square, means velocity square. And similarly, we can write that rotational kinetic energy and we can say this as our R rotational will be equal to over half I omega square, and we can substitute value of our I, moment of inertia, as well as omega. Therefore we get that rotational energy will be equal to over half, and this is over half m r square, and this gives us single dot derivative of the distance and r and whole square. And this r square and r square is going to cancel out, so this will be giving us 1 by 4 m x single dot whole square. Okay. And therefore we can say that our total kinetic energy that is of T will be equal to T translational plus T rotational will be equal to our half m velocity square plus 1 by 4 m, and this is our also velocity square, and this will be coming as our 3 by 4 m x derivative whole square. Now there will be a potential energy, and the potential energy will be associated with the spring. Okay, so the spring is going to store the potential energy. So you can say that the spring stores the potential energy, and let us call this as V. Then this V will be equal to over half kx square, because the spring will be stretched by a distance of x, and because the distance moved by the cylinder is our x, which is our horizontal distance, and therefore we can say that total energy, or we can write this as total mechanical energy that is our E will be equal to our T plus V, and we have this as 3 by 4 m single dot whole square plus 1 by 2 k x square. Now we can make a comparison with our standard you can say the mass spring system, and therefore we can say that for a mass spring system, and the energy associated with this mass spring system, we can call this as E, and we have this as a simple harmonic will be equal to our half and m effective velocity square plus half k x square. And if you make 1:1 comparison, we can clearly see that, let me write the equation which we got is E is equal to 3/4 m square plus half k x square. Okay. And so 1:1 comparison, you can say these will be equivalent terms, and therefore we can write that our 1/2 effective mass will be equal to 3/4 times m, and this goes by 2. Therefore from here we get that the effective mass will be equal to 3/2 times the m. Now we are supposed to find out the frequency of the small oscillation, and we know its standard formula. So you can say that our frequency of small oscillations, let us call this as omega, and omega will be equal to k upon mass effective, that is our effective mass and its square root. And effective mass we already know is our 3/2 times m and its square root, which will be coming as twice k, 3m and its square root. Okay. And we can also solve the same question by using the equation for, or we can say the concept of dynamics. And so let us try that part. So we can say using dynamics, and so we are having that this is a cylinder and a spring is connected to the axle, and k is the spring constant, and the horizontal distance moved by this cylinder is taken to as our x, which is this is the x. Therefore we can say that force on the axle will be equal to minus k of x, and the friction is going to provide the torque. You can say our friction F provides the torque. And once again we have two types of motion, translational as well as rotational. So we can write the respective equations for our translational as well as the rotational. So you can say our translational motion, and translational we have the spring force, that is our minus k of x plus frictional force, and this is mass into acceleration, that is our x double derivative. This is the first equation. And similarly we can write for our rotation, and rotation is friction multiplied by the radius will be giving us moment of inertia, that is our torque, multiplied by our alpha, and moment of inertia is our half mr square, and alpha is our x double derivative divided by r. And so from here we can cancel out this r square, and we get that the friction will be equal to over half m x double derivative. Let us call this equation number 2. Therefore, we substitute the value of our friction from equation 2 in equation 1. Therefore, we can write from equation 1 and 2, 1 and 2, we get this as minus k of x plus half m x double derivative is equal to over m x double derivative. And we can just combine them. We get this as our minus of kx will be equal to, so we take this on the our right side, so this will be minus 1 by 2, 1 minus 1 by 2 will be giving us 1 by 2 mx double derivative. And we can write this in a standard format, that is our x double derivative plus 2k upon m times x is equal to 0. And this is nothing but standard equation for our SHM, and which we can write that our x double derivative plus omega square x is equal to 0. So 1:1 comparison, this gives us that our omega square is equal to 2k upon m, or we can say that our omega is equal to square root of 2k upon, one second, see, minus, this will be our f 1 by 2 minus, and this will be our minus of kx, and this will be 2k upon m. I think something is missing, one second. Kx translational is our f, okay, yeah, this minus of f, and this is minus of f, and this will be giving us our 3 by 2 or 2 by 3, one second. Let's see, plus, so we get that our angular velocity, okay, and from here we can say that our frequency will be equal to omega upon 2 pi, and we can write this as 1 upon 2 pi square root of 2k upon m. So in the both cases we are going to get the value of our 2k upon m. Same question can be asked in a little bit different way, and in this case also we are given that the top of a solid cylinder of a mass m and radius r is attached to a spring of spring constant k, with the spring initially at its natural length. If the cylinder rolls without slipping, find the frequency of small oscillations. Same question, but in this case the spring is attached at the top of this cylinder. So the spring is attached to the top of the cylinder. Spring constant is k and mass is m, and this is the center of this spring. So here also we can use that if we say that x is the displacement of the center, displacement of the center is suppose our x, and we have a angular displacement that is theta, angular displacement is our theta. Therefore we can write that for no slip condition, we can say that our x is equal to r times theta, and if we derivate it, once we get our velocity is equal to r times our omega, and its double derivative, that is a linear acceleration, is equal to r times angular acceleration. And now we know that our center is moving by a distance of x, and the top point is going to rotate by a distance of our r of theta. Therefore we can write that our total displacement of the top point, let this top point of the P. So you can say our total displacement of top point P, and let us call this as our x top. Then this x top will be equal to our x plus r times theta, and r theta is our x. Therefore we can write this as our x plus x, giving us 2 times x. Therefore we can also say that the distance or the stretching in the spring will be stretched by a distance of suppose x spring, then this x spring will be equal to 2 times x. And we can use our energy method, and we can say that we are going to have kinetic energy, and there will be 2 types of kinetic energy. One will be a translational is equal to our half m x derivative square, and we have a rotational will be equal to our half I omega square, which will be giving us our half 1 by 2 mr square, and omega will be giving us x derivative divided by r and its whole square. So the rotational will be coming as 1 by 4 mx single derivative whole square. Therefore the total kinetic energy, let us suppose that is our T. So this T will be equal to our translational kinetic energy plus rotational kinetic energy, and we get this as our half m x single derivative plus 1 by 4 mx single derivative square. This will be giving us 3 by 4 mx whole square, x single derivative square means velocity square. Once again we are going to find out because the spring will be stretched, so it will be having some kind of potential energy associated with it. So we can say spring potential energy, and let us suppose that is our V, so will be our V K X spring, and our X spring is twice of X, so this comes as 1 by 2 K 2 times X, and this is square, so this comes as square, so we get that our V will be equal to, this will be 4, and we get 2x square, 2kx square, and therefore the total energy we have the total energy, and this total energy of E will be equal to 3 by 4 mx derivative plus 2kx square. And we can make a comparison once again with the mass spring system. We have mass spring system, and that is our E is equal to 1 by 2 mass effective x single derivative square plus 1 by 2, and this is our spring constant effective, and we have this as our x square. So we make 1:1 comparison. From here we get 1 by 2 mass effective will be equal to 3 by 4 times m. From here we get that our mass effective will be equal to 3 by 2 times m, and we can also say that our 1 by 2 spring constant effective will be equal to our 2k, giving us that the effective spring constant will be equal to 4 times k. Okay. And therefore we can write that our frequency, that is our omega, will be equal to our k effective divided by mass effective and its square root. So this get our 4k and 3 by 2 m will be equal to, and this comes as our 8k divided by 3m and its square root. Okay, so this is our frequency of our oscillation. And so now in this case, if we assume that we can just generalize this entire question, because we solved the question in two ways. In the first case, we were having that the spring is connected to the axle, and in the second case we solved that the spring is connected to the top. So we can generalize this entire question in a way that, let us suppose that spring is connected at the height d above the point of contact, which is the bottom. Okay. And based on this we can just solve it further. Okay. So let us assume that spring is at a height d above the point of contact. The point of contact. Therefore, we can say that the distance from the center, therefore we can say distance from the center to attachment point is d minus r. Okay, and let us call this as d minus r as our h. So we can say that if this h is positive or greater than 0, then the point of contact will be above cylinder, above the center, and if this h is less than 0, that is a negative, then it will be below center, and if we have that h is equal to minus of r, then the point of contact is bottom contact. Bottom contact. And if we are having that this h is equal to plus r, then it is contact is at top. And rest of the formulation will be our same. So once again, we can say that for no slip condition, we can write that our x is equal to r of theta, r times theta, and its first derivative will be giving us r omega, and its second derivative will be giving us as r and alpha. And if you assume that the transition, the center moves by the distance of x, therefore we can say that the horizontal displacement due to the rotation, and we say that the translational of the center is suppose plus x, and we have a rotation and if it rotates by an angle of theta, and from here we can write that our horizontal displacement due to rotation displacement due to rotation will be equal to over h sine of theta, as the angle is small, so we can say this as our h theta. And we also know that our theta is nothing but our x upon r. Therefore, we can say that rotation contribution will be equal to, we substitute value of theta, so this comes as hx upon r. Therefore, we can say that total horizontal displacement of the attached point or spring, you can say our total horizontal displacement of the attachment point let us call this as our x spring. Then this x spring will be equal to over x plus hx upon r. We can take x as common, so this comes as 1 plus h upon r. And let us call this as 1 plus h upon r as lambda. Therefore, we can say that our x spring is equal to lambda times x, where this lambda we have taken as 1 plus h upon r. Now we come to our energy part, and we have two kinetic energy, translational as well as rotational. So we can say our kinetic energy, that is our T, will be equal to half mv square plus half I omega square. And we already know value of our I as well as omega. So we get this as half m velocity square plus 1 by 2 half, and we have this as mr square, and this will be our x derivative upon r whole square. And we can say that our T will be equal to 3 by 4 mx velocity square. And the potential energy will be associated with the spring. So we can say our potential energy, that is our V, will be equal to 1 by 2 spring constant, and we have this as x spring whole square. And this comes, x spring is our lambda times x whole square. So this comes as 1 by 2 k lambda square x square. So total energy, that is our E, will be equal to total kinetic energy plus the potential energy of a spring. And once again, we can make a comparison with the effective mass system, mass spring system. So we can say that our mass spring system, we can say that our energy E will be equal to 1 by 2 mass effective velocity square and 1 by 2 spring constant, and we have this as our x square. So 1:1 comparison gives us that our mass effective will be equal to 3 by 2 times m, and effective spring constant will be giving us k lambda square. And we know that our angular frequency is equal to our spring constant effective and our mass effective and its square root. So this comes as k lambda square, mass effect is 3 by 2 m and its square root. So this comes as our 2k lambda square divided by 3m and its square root. And lambda we already know is our lambda is our 1 plus h upon r, which can be easily substituted. Okay. And same question, it can be asked a little bit different way, that if the entire system is on the slope, okay, in that case the spring won't be unstretched because the gravitational pull or force is going to stretch the spring. In that case also we can solve using the resolution of the forces. Same question can be done that in that way also. So we have our next question. And it states that a coin of mass m and radius r stands upright on a horizontal table it is given an initial forward speed v of its center and initial spin omega about its central axis, both in the plane of the coin. The coefficient of kinetic friction between the coin and the table is mu. Find the value of v and omega in terms of m are mu g and d. That makes the coin comes to rest, both translationally and rotationally, a distance d from its starting point. Assume that the coin stays in the contact with the table and does not topple. Okay. In this case, the coin is basically moving, and we have to find out that when it travels a distance of d, it is going to stop. So we can just draw an approximate figure. So we are having a coin and its velocity of its center is given as v, and if it is supposed to stop, so it will be rotating in the opposite direction, that is our angular speed omega, and the coefficient of friction is given as mu. And it is said that suppose this is the distance d, from this point it moves, suppose this is our p and this is our p prime, and this distance is given to us as d. Okay, so it stops at p prime. And so as soon as the coin is going to stop, the final speed of its center, that it will be equal to 0, and its angular speed will be also equal to 0. Okay, so it means at this p point we can say our vf will be equal to 0, as well as this omega of f will be also equal to 0. And the force of friction will be acting in, because it is going to provide the necessary, it is going to decrease rather this angular velocity, that's why its final will be equal to 0. Okay. So we can say that we can find out, because there will be two types of motion that will be associated with this coin. One will be the translational, other one will be our rotational. So we can say this as our friction force and as well as torque. And torque. So first is our the friction, and friction is our F, and which will be equal to our mu times our mg, and it will be acting backward at the point of contact. Backward at point of contact, which are nothing but a p, or we can also call it as a p prime. Okay. And therefore we have two types of motion, translational as well as rotational. Therefore we can say that our translational motion and translational is going to force into, force means frictional force, mass into acceleration. Okay. And we substitute value of our friction, that is mu mg will be equal to our ma. So from here we can say that our a is equal to minus mu g. Okay. So negative sign tells us that it is a constant deceleration. So it is our constant deceleration. And now we come to the rotational part. And the rotation, so there will be torque and let us call this our tau, which will be because of a friction times our distance, that is our r, and we can substitute our friction, that is our mu mg times r. Okay. And this will be also equal to our moment of inertia times our alpha. Okay. Therefore, we can say that our alpha will be equal to, we get this as mu mgr divided by our I, and this moment of inertia we can easily substitute. So we get this our mu mgr, and moment of inertia is our 1/4 mr square, which will be giving us 4 mu g divided by r. And now we can use our basic relationship, or we can say basic equation of our kinematics, and find out our final part. Final will be our translational motion as well as our rotational motion. And we know that finally the coin is going to stop. So its translational velocity as well as the angular velocity both will be equal to 0. So we can say we are going to use now kinematics equation, and if we assume that the time taken by this from P to P prime is our t. So if t is the time taken to cover this distance d, okay, so this t is our time. Okay. And we can say that let the time to stop is our t. And first we are going to solve for our translational motion. So we can say our translational motion. We can say that our final velocity, that is a Vf, will be equal to initial and acceleration times t. And final velocity we know that is our 0. Therefore we can say, and we can substitute our a also. So we get this as v minus a is our mu g times t is equal to 0. So from here we get our t is equal to v upon mu times g. So this is the time taken to travel the distance d, or we can say the time to stop. From here we can also find out the distance traveled, which is our d, distance traveled, that is our d is equal to vt plus our half at square. And we can substitute value of our t as well as a. So we get our d is equal to, this is our v, time is our v upon mu g, and this is our plus 1/2, acceleration is our minus of mu g, and this comes as v upon mu g whole square. And this will be giving us v square upon mu g minus, and this will be our numerator will be our v square, and this will be coming as twice mu g. Therefore, the distance d will be coming as 1 by 2 v square upon mu g. And from here we can say that our v is equal to twice mu g times d and its square root. Now we come to the rotational motion and kinematics equation, but in the rotational form. Therefore, we can write that our rotational motion, we can say that its angular omega f is equal to initial plus angular times t, and once again the final angular velocity will be equal to 0, and we can say that this will be equal to 0 and minus of our omega, and alpha we already know is a plus 4 mu g upon r times t, and this gives us that our omega will be equal to 4 mu g upon r, and time we already know is our v upon mu g. So this comes as our 4v times r. Therefore, the angular will be equal to our 4v times r. And we can substitute value of v also here, because v is square root of 2gd. So this gives us omega is equal to 4 upon r square root of 2 mu gd, and this is our value of our angular velocity. And next question, it states that a solid sphere with moment of inertia 2 by 5 mr square rests on a plane inclined at angle of, this would be theta, not mu. The plane is accelerated upward along its surface with the acceleration a, assuming the enough friction to prevent slipping. Find the value of a for which the center of mass of the sphere remains stationary. Okay, so in this case, the entire plane is being moved. So we can just draw the figure, and so let us suppose the angle is given as theta, and we have a solid sphere, and this entire system is being moved by the acceleration of a, and we have to find out the value of our this a, so that this solid sphere is stationary. And we can just divide. So in the downward direction we are going to have our mg, which is going to have two components. This will be a theta, so we are going to have mg sine of theta, and we are going to have mg cos of theta. Okay. And we can find friction will be also there, but we can find out the value direction of friction. Okay. So we have our and this, it is given that solid sphere is stationary, so we can say that acceleration of the center of mass ACM will be equal to 0, or we can say because it is stationary, so net force will be equal to 0. So we can write that our solid sphere is stationary, therefore we can say that our net force will be equal to 0. And if net force is equal to 0, we can write that our mass times acceleration of center of mass will be equal to 0. And from here we can also write that our F minus mg sine of theta will be equal to 0. So we get that our F will be equal to mg sine of theta. So it means the direction of our friction will be opposite to our this mg sine of theta. So it means up the inclined plane. And that will be also resulting into the torque. So we can say that our the torque, and that is our tau, will be equal to our F times R, and that will be equal to I times our alpha. And F is our mg sine of theta. So we can say this as our mg sine of theta times R, and I is given to us is our 2 by 5 mr square times alpha. So from here we can write that our alpha will be equal to, and this R cancel with square, so we get this as 5 and mass goes with mass. So we get this as 5g sine of theta divided by 2r, and this is our value of our angular acceleration. And we are given that there is also no slipping. So we can say we have no slip. So which means that the acceleration of the point of contact should be equal to the acceleration of the plane. So you can say that our acceleration of point of contact will be equal to our acceleration of the plane. And therefore we can write that our acceleration of our contact should be equal to acceleration of our center of mass plus our r times our alpha. And acceleration of contact is nothing but acceleration of our plane. So we can say that our A and ACM is equal to 0. So this comes 0 plus r, and alpha we just calculated is our 5g sine of theta divided by 2r. R and r cancels out. Therefore we get that our acceleration with which the plane should be moving, or entire the slope should be moving, will be 5 by 2 times g sine of theta. So this completes today's session. So today we try to complete the rest of the questions which were left from yesterday's part. Thank you.